Hello, everyone. Thank you for joining today's webinar on fundamentals of soil structure interaction analysis for integral bridges. My name is Jessica Kim. I am in charge of business and support of Midas programs in UK. So our speaker for today is Pere Alfares. He's a principal engineer from Arcadis London office. He has more than 12 years of experience in bridge and structural design, and he has been providing lectures on finite element method at UPC Barcelona for 5 years. So for today, we have more than 1,125 engineers who have registered for today's webinar. And thank you again for your interest and support. So during the session, if you have any questions, please feel free to write them on the questions box on the right side. And our speaker will be able to address them during the question and answer session at the end. So now, Pere, if you're ready, you could start the presentation.
Yes, I'm ready. Thank you, Jessica. So hello, everyone, and many thanks for joining this webinar. So as Jessica mentioned, today's session will cover some fundamentals of solid structure interaction, from the very basics to the application on integral bridges. And I will be presenting a few examples with Midas Civil as well. Please note that this is the first part of a two-part series, and part two will follow shortly. As well as Jessica mentioned, this will be recorded, and the recording will be made available to you. And if you have any questions, I will try to answer them during the Q&A session at the end of the presentation. So, well, as Jessica said, I'm Pere Alfares. I'm a principal bridge engineer in Arcadis, London. I have 12 years of experience and have been involved in bridge and structural design in a variety of different projects, such as High Speed 2, Lower Thames Crossing, Jeddah Metro. And I am often involved in some complex structural analysis. That's maybe because I'm passionate about finite element methods, and especially when they can be used to resolve some challenging problems where other methods maybe they're not able to resolve them. And I believe integral bridges is one of these cases where the finite element method is a good ally to resolve this problem. Let me introduce my company as well. We are Arcadis. We offer global design and consultancy services, and our ultimate goal is improving quality of life. And this defines the way that we work across multiple markets and disciplines. This is also reflected on the bridges team, where integral bridges play a key role on our vision, because integral bridges, as you probably know, offers more sustainable solutions, reduces the whole life costs, and offers increased benefits for our clients. So that's definitely one area of interest. So let's make a start. Hope this is an area of interest for you as well. So for today's webinar, the agenda is as shown on the screen. We will start with a quick introduction on the solid structure interaction problem. Then we will talk about the types of analysis that you can use to assess solid structure interaction. And then we will cover different types of elements which require solid structure interaction to design them, such as flexible foundations, laterally loaded piles, retaining structures, and finally integral bridges. And after that, we will have a Q&A session for any questions you may have. So the first question will be, what is solid structure interaction? Well, solid structure interaction is when the structural and ground displacement are dependent on each other. And that usually happens when the structural stiffness and the ground stiffness are comparable. And when that happens, we need to model the problem with a coupled structural soil model, which takes into account both structural and ground movements. I'm showing the screen some examples. on when you may require soil structure interaction. For instance, in this picture here at the very left, if you have a shallow foundation for a bridge pier or a building, definitely you don't need soil structure interaction. You can design all your structure regardless on the ground movements. Maybe you take into account differential settlements as an input, but you design all your structure, and when you get the reactions, then separately you will assess what are the stress profile at the contact surface with your structure. So that is the case when you don't need soil structure interaction. However, if we are doing something different, something like having a slab on ground where you have point loads, maybe a wheel load, a moving load on top of this slab, and the relative stiffness of the ground and the slab are similar, then you need soil structure interaction to understand how it's going to be the bending diagram for this slab, and then being able to design it. For soft ground, you may have displacement that look more like that. If your ground is stiffer, then your bending moment is going to be more localized. So without the soil structure interaction, you will not be able to resolve this problem. Another example are retaining structures, such as this one here. You may resolve the problem assuming that your retaining element is rigid, and then you can use equilibrium limit equilibrium method. So you ignore soil structure interaction, and you can resolve the problem. But if you start taking into account how your structural element flex and the displacements of the structural element on the ground, you may be able to optimize this design, have more accurate values of the propping forces at this prop level here. Then you will be using soil structure interaction. So typical applications, I already mentioned two of them: the retaining structures, the flexible foundations, but we also have laterally loaded piles, we have integral bridges, we have a big topic that is seismic analysis, which that falls outside the scope of this webinar. So there are many different applications on soil structure interaction. So which types of analysis we have available for us to assess soil structure interaction? Well, I will start with limit equilibrium analysis, which actually is ignoring soil structure interaction and assume that your structure is very rigid, as I mentioned before. By doing that, you can make an assumption on the structure movement as a rigid body movement, and with that, you will be able to assess the stress profile on the ground, for instance, on this retaining wall, on the backfill, and on the front of the retaining wall. And this will allow you to design this element. And same for a retaining structure, assuming that it's very rigid and it rotates along a certain point, you will be able to find a solution to this problem where the stress profiles on the front and the back of the retaining structure are in equilibrium, and then designing the element. So that's a method which is not soil structure interaction, because you are avoiding checking relative displacement between the structure and the ground, but it can be applied on a huge range of different cases. It's relatively straightforward for hand calculations, for spreadsheets. So it's very commonly used. The limitations of this method is it doesn't give you values on the expected displacements. So it's not good for assessing movements of your wall. And usually yields you upper bound solution, which is conservative, which is good. But if you want to optimize, you want to go a little bit further, then you maybe need to use another method. Another type of analysis is the spring analogy. And spring analogy is basically modeling your structural element and then the contact of your structural element with the ground. You model that with springs. And with this method, you are able to both assume the stress profile on the ground and displacements as well. It's relatively straightforward, maybe not as much as the limit equilibrium method, but with simple software, even sometimes with analytical solutions that you can do by hand, you can find solutions. However, it does not provide you results on ground stress distribution or settlements away from the retaining wall. And the last method I wanted to mention here as types of analysis available for you for solid structure interaction is the continuum media. And the continuum media is essentially modeling your structural elements and the ground surrounding your structural element as well. And you can do that with many different methods, but the most commonly used is the finite element method. And this is going to allow you to replicate any complex geometries you may have, different materials that you may have on the ground, ground water flow. So it's very versatile method. However, it's very costly because developing this model is more much more time consuming than the previous two. And being able to define the parameters for your ground model, it's always something quite tricky. So you have these three methods, which all of them comes with some advantages and disadvantages, and depending on the situation that you are on, you may choose one or another. Then let's start with some elements that you may use solid structure interaction to design them. The first one is flexible foundations. And for flexible foundations, you can use the spring analogy using what is called the Winkler model. The Winkler model is nothing else than a model that has your structure as a beam element, which is supported by a series of discrete springs with some stiffness applied to it. This was introduced by Winkler back in the 19th century, but it was not after almost 100 years later that someone formulated the appropriate stiffness for these springs, and that was Terzaghi. And he defined the concept of coefficient of subgrade reaction, which is basically the spring stiffness. Then the spring stiffness, it's not a fundamental solid property, but also depends on the size of your foundation, depends on the stiffness of your foundation, and can be assessed by different ways. It can be done by applied load testing or settlement analysis. But it is a critical parameter to get your model right. So the model that was introduced by Winkler and then Terzaghi defining this parameter is conceived for linear springs, but I've seen many times on the industry taking that and modifying that a little bit, and instead of using linear springs, using compression-only springs, which are springs that are going to take forces only if the structure moves against the soil, but if the structure moves away from the soil and there is no contact, then you don't have any kind of reaction. And I've seen also more complex relations between the displacement and the reaction, which don't follow a linear behavior. These two last examples, what is very important to understand is both of them, they are nonlinear. They're nonlinear springs, but the compression-only springs, they are also nonlinear. The only linear approach is the first one. And it's very important to keep in mind that if you're using nonlinear parameters in your model, then the superposition principle does not apply. And if that happens, that means that you cannot progress with your model the way that sometimes you're used to create a range of different single load cases and then analyzing them separately and combining them in the post process. If you're using nonlinear springs, you are not able to do the superposition anymore. So that means that for every single different situations that you may have, you have to run a single load case with all the loads that you have in your system. And that's for, at least on the for design purposes, that might be impractical sometimes. Now we're going to jump to laterally loaded piles. And laterally loaded piles is a very similar situation as the flexible foundations. They can be resolved by using the Winkler model again. And in this case, there are two main approaches for using the spring analogy. The first one is using a coefficient subgrade reaction, similar as the flexible foundations I mentioned before, which is basically linear springs. And the other one is using PY curves. And the PY curves, we're going to talk a little bit later, but they're basically using nonlinear springs. The Syria R103 says that the computed bending moments are not very sensitive to the parameters that you're using for the spring, but the flexions, they're roughly proportional. So that means that if you're using a spring analogy for your piles because you're after the bending and shear diagrams, maybe choosing the right parameters for your ground is not that important as far as you get something in the ballpark. But if you are after the deflections that you may have on your pile, then getting your ground parameters right is much more important. So the first approach, the linear springs using the coefficient subgrade reaction, similar to the flexible foundations. As I said, this is not a fundamental soil property. That also depends on the pile breadth. It depends on the stiffness of your pile and can be assessed by different ways. Correlation of soil properties with another site that you know how that has a similar ground conditions. In situ tests with different tests like bed load testing or SPT, or you can build a pile and test it and see how it behaves under horizontal loads and use the results to then use it for your design. There are two main ways of defining this coefficient of subgrade reaction for laterally loaded piles. The first one is with a constant parameter, which is often used for cohesive materials such as clay, and another one that is increasing with depth. That this is the one usually used for cohesionless materials such as sands. Terzaghi defined some typical values for these springs for both clays and sands. They are summarized on the Syria R103. And depending on, Terzaghi defines three types of clays and three types of sands with expected values for this coefficient of subgrade reaction. As I said before, if what you're after is getting the bending and shear diagrams on your pile to design the reinforcement in your pile, maybe using one of these parameters that's accurate enough to get a reasonable diagram. If you're after deflections, well, that's going to be a good starting point, but maybe you need to do additional tests to get the right parameter. So that was the first method. The second method is PY curves, so nonlinear springs. And PY curve, what basically means is a curve that defines the relation between the force applied to the soil, P, and the lateral deflection, Y. And there is a large number of different authors that have defined PY curves for different situations and different ground conditions. And there is a sentence in the Syria 103 that I really like, says that the PY method has insubstantial theoretical background. In fact, all these curves have been derived using empirical methods and testing piles on site and see how they behave. But the good thing is they have been massively used, and they have proven to be a really useful method for designing piles. As far as you know that the data that you have is relevant for your situation. So it goes down to your own judgment to decide if using these PY curves is something appropriate for your project and your case or not. Here I'm showing two different curves, one for sands presented by Rees, another for stiff clay presented by the same author. But I wanted to show you as well that there are PY curves for static loading, but we have also PY curves for cyclic loading because they have been piles tested maybe on site to see how they behave after a number of cycles. And they have also been proven to be very useful. So now I wanted to show you an example of how to design a largely loaded pile with Midas. So it's a really simple example just to demonstrate the principles behind this case. So we have, for instance, a bridge pier foundation with a pile cap and several piles, and we want to analyze one of these piles with one horizontal reaction because we want to design the reinforcement and we want to understand what is the bending and shear diagram. So what we are going to do is model this pile. In this case, just for demonstration purposes, I'm going to use a model modeling this pile twice. Once for linear springs with a coefficient of subgrade reaction, another one with nonlinear springs with a PY curve. So I'm going to show you that now. So we have a model like this one, the one on the left, as I mentioned, this is linear springs, and we have another one on the right with PY curves. And the main purpose of this example is to demonstrate the importance on the parameters for deflections and the importance on the ground parameters for bending and shear. So we have two different methods for analyzing this pile, which is modeled as a beam element, is supported vertically on its tip, and is fixed for rotation at the top because this is attached to a pile cap that will prevent the pile to rotate. Then at all these intermediate nodes, we will have linear springs on the case on the left and non-linear springs here on the right that will basically model the ground reaction against the pile when the pile tries to move against the soil. So as I said, linear springs here on the left, on the right, just for showing you how one of these PY curves looks like on this model. Every of these nonlinear springs have movement against reaction relation like this one. This is defined by a series of linear segments. And you can see that initially you will have some elastic response, but very quickly the ground will soften. And the more that we push the ground, we'll get a softer behavior until we reach the maximum reaction that we can expect. This obviously is different at every level. We'll reach a yielding of the ground much quicker if we are close to the surface. The further deep we go, the resistance we can expect is much greater. So we have to define one of these curves differently for every single level. If we do that and we run the analysis, then we can check the results. First thing I'm going to check is deflections. And then we can see that the flexions on the linear springs, we get 50 millimeters. And the one using PY curves, we get in 10 millimeters, which is a substantial difference. It's 50% more in one case than the other. However, if we are modeling these piles because we want to design the reinforcement, we are not after the displacements, we are after the bending moments. After the bending moments. And for the bending moments, we see that the one using linear springs, we get a value of 1430. For the PY curve, we get a value of 1350, which are relatively similar. So we just able to confirm that the bending moments, and that will be the same thing if we check the shear diagram, are not that dependent on the parameters that we are choosing, but if we're after the displacement, the parameters and the appropriate model is much more important. So that was what I wanted to show you in this example. Now let's talk about retaining structures. That's another case where soil structure interaction is very relevant. And the first concept that I want to introduce is lateral earth pressure. So lateral earth pressure is the pressure applied by or applied to the soil when it's against a retaining structure, such as this one is retaining this soil at the right. So we have a pressure applied to the structure, or the same pressure is applied to the soil. And a very common way of defining this pressure is by multiplying the vertical stress on the soil by a coefficient which is called the coefficient of lateral earth pressure, which is this KV here. And now the question will be, how do we assess this coefficient? Well, this coefficient, as you probably already know, but just a refresher, depends on the situation that you are with your retaining structure. So if it's a retaining structure that you are not expecting it to move, then you have a situation that is called at rest. The Eurocodes give you which are the deflections that you can assume that they are negligible. And when you have barely no movement on the wall, you had some coefficient like this one. It will depend on the ground conditions as well. If your structure is moving against the soil, then we have a situation that is called passive resistance, and that happens after the structure has moved a substantial amount against the soil. Then the horizontal pressure on the soil increases significantly, and we get this Kp here. On the other hand, if your structure is moving away from the soil, the horizontal stresses drops, and we have the situation that we call active situation, which is this one here, and shown on the graph here, which is reduced from the at rest and passive resistance. There is different formulations for deriving these three parameters, such as the ranking theory, and the Eurocode is giving a little bit more comprehensive formulation for these values. But the important thing to understand is these three parameters there for when your structure doesn't move at all, on when you have substantial movement, so you're able to mobilize all the passive resistance of the soil, or when you move your structure away enough from the soil, so you mobilize all the active resistance of the soil. But that doesn't give you an idea on what happens on any intermediate values if your structure doesn't move enough to mobilize the passive or active resistance. In order to do that, the Eurocode is very flexible. It says that this may be calculated using empirical rules or spring constant methods or finite element methods. So you really are able to choose the method you think that is more appropriate. One thing that I've seen very often in the industry is using elastoplastic behavior. So from the passive resistance, then you assume linear behavior between passive resistance and the active resistance, having the at rest pressure on the parameter that you already know. That's one way of doing it. Another way of doing it is on the Annex C of the Eurocode 7. Tells you that you can still use linear interpolation between the at rest and active pressures, but then you have a curve to be interpolate between the at rest situation and the passive situation. So there's two different ways of being able to assess the soil stresses on these intermediate values of movement of your wall. Now I wanted to introduce another example. That's a retaining structure for an excavation here on the front, and we have an homogeneous material. Obviously, I'm keeping everything very simple for the purpose of demonstrating how it works. In the real world, things get more complicated with different stages and different strata in your ground. But let's assume that we have a homogeneous material, a medium dense sand, and we want to replicate this this stress profile at the back of the retaining structure and front of the retaining structure with the concept that we have just introduced. And what we can do in Midas Civil is we can start with assuming that you have an external load equivalent to the at rest situation, assuming that the wall doesn't move. But obviously, that's not in equilibrium, because if we do that, then the forces on the back of your wall will be much greater than the forces on the front of the wall. So if that happens, your retaining wall will tend to move, and when it starts to move, it will start mobilizing this active and passive resistance. And how they're going to look like? Well, possibly they're going to look something like that. So on top of the retaining structure, on the backfill, since your retaining structure is moving away from the retained soil, then your pressure will drop from the at rest to an active situation. On the front of the retaining structure, since your retaining wall will move against the soil, the pressures will increase from the at rest to a passive situation. But there will be some point here down on the retaining wall that you will have no movement, because there will be a point of rotation. So it's going to be something like that. And when that happens, both the front and back soils you'll be expecting to have at rest situation, because there is no lateral movement on the ground. And below this point, then you will have the opposite situation, where you have active soil resistance on the front of the retaining wall, and you will have passive on the back. But how we can model this this situation, which is not the initial external load that we have introduced as at rest pressure, how we model these variations that depend on the movement of the wall? Well, what we can do is adding a series of nonlinear springs that represent the increase or decrease on the earth pressure to reach the passive and active situations. And this nonlinear spring will look something like that. So when there is a lot of movement towards the soil, we'll be increasing the horizontal stress until we reach the passive situation. At the contrary, if our retaining structure is moving away, we will be subtracting forces on the at rest situation until we reach the active situation. In order to do that, we will need to set up the parameters for our model. So as I said, we have a medium dense sand, and I'm going to assume a number of parameters. As I said, I'm keeping things simple because of demonstration purposes. I've assumed these values here for K0, Ka, and Kp, which maybe you say that is not representing any real material, and maybe it doesn't, but just is to keep the figure simple. If we are doing that, this is going to tell us which are the soil pressures that we can expect on active, at rest, active, and passive situations on these three columns here. So if the retaining structure doesn't move at 1 meter depth from the surface, we can expect horizontal stress of 10 kilonewtons per square meter. If it's active, 5. If it's passive, 60. Obviously, that depends on the depth. The more we go down, all these stresses increase up to having, for instance, at rest 150 or 600 here. The other thing that we need to take into account is we are going to model these springs with the elastoplastic approach I've mentioned before. And this elastoplastic approach, since we are using sands, cohesionless material, it will change with the depth. So it will start with 5,000 kilonewton per cubic meter at 1 meter of depth, but this will be increasing as we go down. So how we translate that to these nonlinear springs that we have to introduce to our model? Well, what we need to do is the linear spring to add or subtract from the at-rest pressure the amount of pressure to reach these two different states. For active, we have to subtract to this 10, we have to subtract 5, so we get the active state of 5. So it's going to be this value here. For reaching the 60 kilonewtons per square meter on the passive state, we need to increase the reaction on the nonlinear spring by 50. So on the first meter, we'll have a nonlinear spring that looks like that. That goes, if the movement is towards the soil, starts from 50, and then we have a linear behavior around the at-rest situation, and then on the active situation, we have -5. This is different if we go down. Every level will be different. The last spring at 10 meters depth from the surface. The passive, the increase for reaching the passive situation will be 500 kilonewtons per square meter, for instance. So now I'm going to show how this looks like in meters. So it's a very simple model, similar as the previous below that I presented before. It's an element that is representing 1 meter strip of your retaining structure. It's 500 mil thick, and it has nonlinear springs at 1, 2, 3 meters, etc. Then the first thing that we need to do is adding the at-rest pressure. But we know, as we said, that this is not in equilibrium. And then we also add these nonlinear springs. And as I introduced you already before, every of these nonlinear springs look something like that. Starts from 0, and if the movement is away from the soil, you have a negative value. If it's moving towards the soil, it has a positive value to replicate these active and passive situations. So if we run this analysis, we'll get some results. And if you're checking, for instance, the reactions, we'll see that we have on the first spring a reaction of 5 kilonewtons. And that's basically because we have substantial movement away from the soil at the top of the retaining wall. So the initial 10 kilonewtons per square meter, the at-rest pressure that we have introduced as an external load, we subtract 5 kilonewtons per square meter with a nonlinear spring. So the result is 5 kilonewtons per square meter, which is basically the at-rest situation that we were looking after. So that's happening for the first meters, and then we have some intermediate values when we are not able to mobilize the full active or the full passive situations. And basically, Midas runs this as a nonlinear analysis and finds a solution where the stress profiles are in equilibrium, and with that we are able to assess the deflections of the wall, and we are able to assess, more importantly, the bending diagram, so we can design this wall. Right. So that was another example on how to use solid structure interaction using the spring analogy. And finally, let's talk about integral bridges. The question will be, what is an integral bridge? I'm sure that all of you know that, but just a refresher, just to ensure we are all on the same page. Conventional bridge is if you have a deck that is supported on bearings and has expansion joints. So when you have all the seasonal changes of temperature, and you have expansion and contraction, this deck is free to move. That's why you have the expansion joint, and there is a very limited amount of reaction that is transferred to the abutments. However, these bearings and these expansion joints has been proven to be tricky details. They require a lot of maintenance, and around the world, all the authorities are encouraging the designers to use integral bridges to remove these bearings and these expansion joints and reduce the whole life cost, and has proven to be very beneficial. But it comes with an increased difficulty is by having this monolithic connection here. When we have expansion and contraction, that basically means that not only the deck expands and contracts, but also that happens with your abutment wall. And when that happens, if you have a granular backfill behind the abutment wall, this cyclic loading and unloading, this cyclic movement that you get from the seasonal changes starts compacting the soil behind the wall with a phenomenon that's called soil ratcheting. And when that happens, the stresses that you get on the backfill of your abutment increase with time. When you have on this graph here, you can see at the first cycle, you can get a stress profile like this one. After 3 cycles, this has been increased a little bit. After 10 cycles, this is even more. And this keeps increasing for the whole service life of the integral bridge. So it's very important to have a realistic estimate of these stresses, because this is going to have a major impact on the design of your bridge. Then on the PD 6694, all these plenty of recommendations on how to design integral bridges, and basically defines 2 different scenarios. One where you don't need solid structure interaction, and another one when you need solid structure interaction. The first one is you can use limit equilibrium method, similar as the method that we have already introduced, and you can use that when you can easily predict when will be what will be the depth of the soil that will be affected by the abutment wall moving against expansion and contraction. But and that usually happens with full height abutment walls with spread foundations or bank seat abutments. For instance, on bank seat abutment, you can easily predict that the movement and the depth of the soil that will be affected by the deck movement and the bridge movement will be this one. So you don't really need a soil structure interaction to identify this. However, in other cases, this is not easily identified what is going to be the depth of the soil that is going to be affected by the deck expansion and contraction, such as continuous pile wall abutments, such as this one. So we have expansion and contraction. This is going to expand, and then the piles, they're going to follow that, but we don't know exactly until which depth will have the effects of this soil racketing, of this cyclic loading. And to assess that, we will need to do a solid structure interaction. So let's start with the limited equilibrium methods, the ones that you don't need solid structure interaction, and you can resolve them on a straightforward way. PD 694 differentiates 2 different situations. The first one is when the movement is purely by translations, such as the bank seat abutment I just mentioned. And when that happens, you know that the soil profile and the movement that you can expect on your structure is something like that. And then you can assess the soil racketing effects by using, instead of a passive of active or at rest coefficient of earth pressure, using this K star. And this K star is coefficient of lateral earth pressure, taking into account the effects of cyclic loading. Another case is if the movement is not by translation, by rather rotation and flexion of the retaining structure. So if your retaining structure rotates like that when there is expansion, then you know that the depth that will be affected by the movement is going to be something like that. And then instead of using an at rest profile for the horizontal stresses on the backfill, you use the modified one, which is this one, increased by the soil racketing effects and defined by, again, K star, which has a slightly different formulation for this case on the PD 6694. So that's the two cases where you can avoid soil structure interaction and you can resolve the stress profile on the back of the abutment. But what happens if you cannot predict easily what's going to be the depth of the soil affected by this expansion and contraction? Well, then you need to jump to a soil structure interaction. For instance, on this one, you have some expansion on this figure on the top, and then the depth affected by this expansion goes further down. It's not limited to the height of the abutment, but goes further down. And we need to understand what is this depth affected by the movement. And for the contraction, something similar, because now, since this depth is likely to be deeper than the height of your abutment, will affect not only the backfill, but it's going to affect the ground on the front of the abutment as well. So what we want is to assess these stress profiles, which take into account the soil racketing effects. On the PD 6694 says that you have to consider many different things, like the nonlinear response of the soil, the effect of the strain racketing, but also the soil arching between the piles, if you have the piles with some spacing but still quite close, and is flexible enough to give you the opportunity of use the method that you think that is more appropriate. However, it introduces you a specific method that can be used for resolving this soil structure interaction problem, and this is given on the Annex A of the PD 6694. And this method, the first thing that it does is explaining how you can derive the soil properties taking into account the cyclic loading. And I'm not going to go into detail, but basically with the vertical stress, you can derive the mean stress, and with the mean stress and this factor here, this is variation in the soil shear modulus factor, you can derive the soil properties. The problem is to get this factor here, the variation in soil shear modulus, you need to know what is this this movement of the wall, which is represented by this D and this H, which is basically the height of the ground affected by the movement and the movement of the wall at half of this depth. To this, we need these two values to derive the soil properties, but we don't know with these two values because we need to run the soil structure interaction problem. And the question is how we will resolve this, and the answer is doing an iterative process. So if we are deriving the expansion case to derive the stress profile behind the abutment, the first thing that we need to determine is the movement of the deck. Then we make an assumption on these values, the depth that is going to be affected by the deck, the abutment movement, and the movement of the wall. With this assumption, then we will be able to derive the soil properties. And with the soil properties, we can first apply contraction and then apply expansion and check until with depth we have increased stresses. So if I go back to this figure here, this is the soil stress profile that we can expect from a conventional retaining structure, but due to the soil racketing, we have an increased stresses due to the cyclic loading, and this affects up to a point here. And when these two situations meet, that's you define that as the height of the soil affected by the movement. So when we are able to calculate these two values here, then we can compare with our initial assumption of these two values that we have already done at step 2. If they're relatively similar, job done. If they're not similar, what it means that we need to recalculate the soil properties again and redo the analysis until we get conversions between the soil properties that we are using and the parameters used for the soil properties and the results that we're getting from the analysis. That's for expansion. And then we have something similar for contraction. So I wanted to talk about how this is used for how PD 6694 introduces these methods for interior bridges, and also wanted to mention all these previous methods for laterally loaded piles and retaining structures, because they are fundamental for then resolving interior bridges. As I mentioned, this is the first part of a two-part webinar. On the second part of the webinar, we will be covering a detailed example on solid structure interaction applied to an integral bridge. So unfortunately, I'm going to skip a couple of slides I had prepared for you because of time constraints, and I will jump to the question and answer sessions. So if you have any questions, you may write them on the questions menu on your GoToWebinar application, and I will try to respond them. So I'm going to check which questions we have at the moment. If asking if the presentation will be able to be shared with you, I understand that the presentation will be made available to all of you together with the recording. One question is, what is the effect of using clay behind the abutments as opposed to granular material? And according to the PD 6694, what it says is the effects of soil racketing on cohesive materials are negligible. So you only need to do all this iterative process and soil structure interaction analysis and the case study if you have a cohesionless material behind the wall. Let's see other questions. How to obtain the displacement to be defined in the nonlinear spring in Midas? Well, that depends on the nonlinear spring model that you're using. If you have PY curves, you have the formulations on the Syria R103, or if you're using retaining structures, you will have the values on Annex C. Other questions? For the PY curves, I've seen you have used the force deformation function. I'm not sure if that's a new feature from Midas, but in the past I have used multilinear point spring supports, which also lets you define the PY curves for each pile node. will these two ways we define a solid structure interaction have the same effect? I think the answer is yes. I think before you were defining these curves per single spring, and I don't remember exactly which version of Midas allowed you to create a function independent from the spring that you can define this PY curve or the nonlinear spring curve that you want to define, and then use it in one spring or multiple springs as you see fit. So yes, that's a new feature, and it has the same effect as using specific nonlinear curves for every single spring. What are the solid data required to develop PY curves in Midas Civil? Midas Civil has some functionalities to assign PY curves directly in your elements. And therefore, I will try to cover that on the second part of the webinar. However, you are able to define any kind of nonlinear spring that you want, because you're able to create any function between displacement and force that you want. So it's entirely up to you. Another question is, could you please provide background information as why superposition principle doesn't apply when using nonlinear springs? I think that's an important point. I will try to show that in another example I had prepared, but I didn't have time. To show due to time constraints, but I'm going to try to show you now why it's important not to use superposition principle when you're using nonlinear springs. So this is another example I had prepared for you, which I didn't cover at the end, but is flexible foundation. Is a slab, and I have same as the piles. I have modeled the slab twice, one with linear springs and one with nonlinear springs. And then I'm applying a force at almost the edge of the slab, and we have another load case, which is the self weight. And just for your information, the linear case is the one on the right. The nonlinear case is the one on the left. Right. If we do that and we check the results for, I'm going to go jump directly to beam diagrams. No, let's check reactions first. We have our nonlinear and linear springs giving us the same results for the self weight as a separate load case. For the life, for nonlinear springs, I'm only getting compression results on these springs here, but I'm getting compression and tension results on this other one. And you might think, well, that's not realistic, because if there is no contact here, you shouldn't expect these springs to be in tension. But the truth is, the load case that you want to consider is not only self weight or only this point load, but the two combined. So if we're checking combined results, then we have different results if we are considering the nonlinear springs here on the left and the linear springs on the right. Sorry, if we are using combined a combined load case, which has the two load cases, self weight and the point load, you will get the same results. So that's fine, and I'm not getting any tractions at any point, so we are happy with our assumptions. However, if instead of using a combined load case, which has both the cell weight and another load, I'm calculating independently cell weight, another load, and then I'm using a linear combination, then the results are quite different. Because the linear springs will add and subtract the cell weight and the point load. But will not happen the same with the nonlinear springs. And then when we are getting the bending diagrams, the bending diagrams are going to look very different. because the cell weight will act as a pre-compression for the springs, and then for on this case, you have a more distribution of the load. In this case, is less distributed. So this one is the correct one, and this one you see that if you combine with linear combination or you do a combined load case, you get different results. So you have to be very careful about that. Okay. So I can see that there is plenty of questions. I don't have more time to go through all of them. Please, if you have any further questions, send an email to Midas support, or maybe you have the opportunity to ask them as well on the second part of the webinar. Thank you very much for attending, and now I will hand over back to Jessica. Thank you, everyone.
Okay, thank you, Pere, for the presentation, and thank you for all the attendees for joining today. So as Pere mentioned, the recorded webinar video and the presentation materials will be shared to all the attendees, and you could also find the video from Midas YouTube channel. So for any further questions, please feel free to contact us to info@midasit.com. And for the users from UK, you could also contact us to uksupport@midastuser.com. So thank you very much for the time today, and we'll be ending the session now. Thank you.